Okay, hello everyone to this video slash talk slash lecture, whatever you call it. Um, so in this video, just when I say lecture, we'll talk about the k-epsilon models. Okay, so if you don't know, this is the two equation models, the two variables k and epsilon for CFD applications. Now, so when I say CFD, I do mean Computational Fluid Dynamics. Okay, so we're using numerical modeling techniques to measure fluid properties around a mesh. Okay, so yeah. Now, the reason I want to do this video is because as I spent some time being a teaching assistant in my master's, and I've noticed that there is a lack of knowledge where students, especially at the undergrad level, don't know what turbulence models they should use for their problems, for their dissertations, for their projects, whatever they're doing, they're not sure what model to use. And, like even when I said here, I've seen some students at a master's level use highly turbulent, use lambda models for highly turbulent, highly rotational flows for the simulations. And, the more you get into this, so we say engineering study, you'll see why this is just wrong. And even then, you just have to have a basic grasp on why laminar models will work in turbulent flow in highly turbulent flow, because it doesn't simulate everything. But I digress. This is why I'm gonna do this video, is just to clarify what epsilon models you should use for your simulations to reach the most accurate results. Now, please remember that CFD is a tool. It is not the final solution. Yeah, never is the final solution. And it is pretty common to see that CFD solutions are off by 5 to 20% compared to real world applications. So, for like you'll see supersonic flows is off by 20% easily. Yeah, but that's very standard because of the chaos nature of turbulence. Yeah? So yeah, that's it really. So we'll get started. Okay. The standard k-epsilon model. I think most people are aware of this model. It's from the 1970s. It's highly talked about in a lot of literatures. You'll see if you just Google the epsilon model, k-epsilon model into YouTube. This is the first model that comes up with. Yeah, so it's from the 90s and from the 70s, 1970s. Created by Jones and Lauder and many other people, by the way. But these are two of the main people who had some serious input to this two-equation model. Now, this model is based on empirical and fluid phenomena data. Okay, so Lauder and Jones wanted to improve this model to create a model that was better than the mixing length concept model. Okay. In some literatures, especially like these, yeah, Introduction to Fluid Dynamics, Finite Volume Method, and Numerical Methods for Engineers and Scientists, it talks about the Prandtl's one equation model. Yeah, so it's just one equation. That's the turbulence. Yeah, that's the K. Okay, and other algebraic models. I'll be honest. Not many people use algebraic models anymore, unless you write the code yourself. Yeah? In Fluent, you won't see this unless you write the code yourself. Okay, and if you really want to know what these are, I recommend they're actually interesting. They're not accurate, but they're interesting. See CFD Online. Yeah, it's a great online web source. Now, this model is very popular because of the robustness. Yeah. It's cheap, like it's super cheap to do, and it's pretty accurate. Yeah, not DNS accurate, but still pretty good. Yeah, it's cheap because of the simplifications of the fluid dynamics. Yeah, you'll see. Like I'll talk to you about this, but the simplification of the eddy viscosity. Yeah, and I'll show you what that is later on. Yeah, obviously nothing is accurate as DNS. Nothing whatever will be unless we solve this directly, but it's pretty accurate for certain applications. So many companies have used this model for years. Yeah, because it's so cheap, and it is accurate, and it does the job. You know, it's best bang for your buck out there. Okay, so let's talk about what these mean. Okay, so the K is the turbulent kinetic energy. Okay, you know, and the epsilon is the dissipation of that energy. Okay, so it's per unit time. Okay, I'll show that later. But we know as engineers, and I'm an engineer myself, an applied physicist. When I say applied, I do not mean like space engineers. I do mean like meteorologists and so forth. The scales that we only care about are 10 to the minus 6, so millimeters, to the scale of modeling weather. Yeah, so hundreds of kilometers. So basically, you know, that area of fluid dynamics, we use Newtonian physics, yeah, to model the properties. So there has to be a conservation of energy. Yeah, hence that's why there's an energy term in the equation. Yeah, and it actually makes sense if you think about it. Like if you add energy to a system, there has to be energy in there somewhere, and we're just trying to model that energy. Okay. So the energy term is used to close the Navier-Stokes equation after the Rand's averaging. Okay, but it's just turbulent energy. Yeah? And like I said, the epsilon is the rate of dissipation of that energy. So, and if you look, yeah, so this is the standard equation. Yeah. Obviously, rho is density, TKE. This is given in Einstein summation notation, which is it's not vector formation. And you will see in most cases, in most books, you'll see it as Einstein summation notation form. I think it looks nicer. B, I think it's easier to read if you are from a more engineering background. Okay. So this is the dynamic viscosity. Yeah, and see this mu t. That is the turbulent dynamic viscosity, or it is sometimes referred as eddy viscosity. I don't like that. I prefer dynamic viscosity, turbulent dynamic viscosity. It's a little better. Oh, I don't know what happened there. And this is the Prandtl, turbulent Prandtl number, I should say, sorry. And yeah, so you have GK, which is the generation of TKE due to the mean velocity gradients. The generation of TKE by buoyancy. And this is the dilation of flow for compressible flow and its dissipation rate. Okay. Yeah. So if you don't have, if your flow is incompressible, this will go to 0. If it's compressible, this will have a value, and it's used to solve this. And these are the source terms. So if you have a source term for the flow, this is where you would add it in. Yeah. And yeah, this is the dissipation equation. Yeah. So you got the dissipation here. Literally almost everything similar. Yeah. Except you got a few model constants. Yeah. Just to simulate the dissipation better. So. And I want everyone to notice the equation. Yeah. It's actually TKE per unit time. Yeah. It's the energy per unit time. Yeah, that's the dissipation. Okay. And now we're gonna see how it's different from the other models. Okay. So it actually, one of the main reasons it's different is actually the way that the other models are different. It's the way that uses the models for eddy turbulent viscosity. Yeah. So if this is a constant, this will be taking the other side. Yeah. But if it's not, it'll stay on this side. This is actually a constant here, 0.09. This is actually a problem. We'll see why later. And once you find this is closed, and we can solve everything. But it's because the simplification of this turbulent viscosity this is quite poor at certain applications. Okay. Now let's move on to the RNG. Now, the RNG does not stand for a random number generator. I've heard of this a few times. It's not true. It actually means the renormalization of group. The theory is very complex, and it is way beyond the scope of this video. Yeah. But if you are interested, just do a word search and this is the original paper, Renormalization Group Modeling of Turbulence Simulations by Ozark Stephen A. 1993. Yeah, your reference at the bottom there. So, okay, if you look, so this is the TKE, yeah, this is dissipation. Exactly the same units. But you might notice one thing. Apologies for my phone. You might notice one thing. It's different. It's this value. Yeah, if you look up, this value is this. So if we model the turbulence, the dynamic viscosity, the turbulent dynamic viscosity differently, yeah, and the Prandtl number differently using this. Yeah? So obviously there's more constants. There's with this flow, but you know, at the end of the day, it's still solving the same equations. And again, I cannot iterate enough how complex the theory is. Yeah, it's not something as engineers we're used to this way of thinking this mathematically. But anyway, I digress. And so obviously I talked about this term. Yeah, that's different. So that's it. It closes, it models another way to solve for mu t, so turbulent dynamics viscosity, Prandtl number, and so forth. And you got more constants in the dissipation. So, you know, these people have found out like the dissipation is not great for this model, especially around swirling, around swirling eddy, like swirling machinery, that's it, swirling machinery. So they decide to add a few terms, change a few things, and one main thing I want to add is this RE term. Yeah? RE epsilon, I should say, sorry. This term is very simply put. For low to moderately strained flows, the turbulent eddy viscosity values will be closer to the standard model. So this model, yeah, the eddy viscosity will be modeled using this. Okay? So I like to think of this as a 0 or 1 switch. It's not exactly, but it helps me think, and helps a few other students think too. So if it's low strained, go back to this. If not, do the full thing here. And you'll realize for highly strained flow, it uses this model instead. Yeah? The equations are pretty complex. You know, if you really want to look at the fluid theory, but for the scope of the video, it's just a very quick video on how to, where and why you should use it. Yeah? So high curvature, so think RNG model is the mesh really high curvature. Yeah? You should really use this. Yeah, look, so for highly turbulent Reynolds number flow, you literally use the same equation, but the constant C mu is different. Yeah, it's off by 0.005. Yeah, that's it. But you might say to yourself, oh, you can change this number in Fluent. You should change it if you click the standard. No, you should not change it. Yeah, you should read the literature. Yeah, this constant is pretty solid for this model. And this number is pretty solid for this model, the RNG model. Okay. Now, for low Reynolds number, this is where it gets confusing, in my opinion. You're actually integrating this, yeah, and uses inverse effective turbulent Prandtl numbers to solve, and it's literally by using the RNG theory to solve for the rest of the equation. It's quite complex. Again, it's not the scope of this video. I like mathematically speaking, it's pretty heavy. So if any mathematicians are watching, let's spend some time. You can teach it to me. That'd be great. If not, no worries. Yeah. Now let's talk about the final and the last model, the realizable k-epsilon. Okay. So this model is 1995. Yeah. So it's by far the newest k-epsilon model, the most popular k-epsilon model. Okay. So this is about 1980s ish, 1995s, yeah. So this model is here really to address the horrible shortcomings with the dissipation term. Furthermore, it models eddy viscosity or turbulent viscosity a little bit differently. Several authors and empirical data find that jet flows, yeah, when you have a plume of jet, the dissipation rate of the jets actually do not match the real world data. So a new model was needed. So Shish, I'm sorry if I butchered that last name, but proposed a method. Instead of using the turbulent viscosity as a constant, it is actually computed. Okay, here. So these are computed. They mean nothing. Yeah. The one thing that's very important to us is this term. Yeah. Oh, I don't know what happened. Oh, yeah, it is what it is. Anyway, I'll leave it. Give me a second. Delete. Redact. Oh. It is what it is. Okay. So, like I was saying, it's this term. It's computationally done. Instead of users giving an input, yeah, it's computationally done. So, this U star is identical to the angular is proportional to Sij, so it's the mean rate of strain tensor, and the vortice tensors. And some students do get this confused by SKK because I and J are there. It's not the same thing. If it is, it will actually be zero in incompressible term, which is not true. Yeah, obviously there'd be dissipation in incompressible flows, but I digress. Yeah. Also, yeah. So look, this is actually identical to the standard k-epsilon model. Yeah, but it's different because the way it computates the turbulent viscosity, yeah? Using the mean rate of strain, the vortices and stuff like that. Okay, so I've talked hopefully for long enough. So I'm going to conclude. Yeah, I'm going to conclude. So the standard model is fast and it works reasonably well away from the walls and in some sonic flows. Yeah, but the model has some serious limitations, such as near the walls, high curvature of surface areas, and where the fluid separates. Okay. Furthermore, the standard model cannot model laminar or low turbulent Reynolds numbers effectively. Yeah. So if you use laminar settings, the model gives up. You will get horrible results. And low turbulent, I have seen this myself personally. In low turbulent Reynolds numbers, it does not work properly either. So there's other models you can use, but the standard one does not work. Okay. Some common flow model uses are flow properties over flat plates, such as airfoils. Again, it's fine. The flow properties cannot be near the walls. Okay. Internal flows. So this model, like if this model was used for one thing, you have to use it for pipe flow. It's really good for pipe flow. Obviously, when it gets closer to the walls, it becomes a little bit iffy. But overall, pipe flows, it's magnificent. Yeah. It has been used for a while for turbulent mixing, combustion, and species modeling, because combustion modeling is very expensive. It takes a lot of time. Species modeling it's very expensive. So if you have a cheap computational fluid model, yeah, it just helps bring down the cost. Yeah. And environmental flows. However, this actually does depends on the complexity of the environment. So let's say you would use this model if you're modeling wind around in Dubai, with multiple skyscrapers, but maybe in a small city, it'd be better. Yeah. Now, the RNG model is a great model for the shortcomings of the standard model. It produces accuracy really well for highly strained flows. Okay. So think like turbo machinery. Okay, compressors, turbines, and so forth. Also, it can actually, and it is pretty good at predicting the flow properties from laminar to highly turbulent fluid properties. So think all Reynolds number scales, yeah? And it is actually considerably better at this than the standard model. But however, this model is, again, quite poor near the walls, yeah, if the treatment is not applied properly. So when I say the treatment, in Ansys Fluent, there is an enhanced wall treatment, which is another set of equations and what forth to help to get proper results, So you should use that if it's high wall, if you're finding properties at the wall and at the free stream free stream velocity parameters. But the k-epsilon SST does a little bit better job of that. That's another video. I'll make it in due time. Also, personally speaking, this is understanding the theory, is difficult. It is not easy. I recommend that you have a look at it. If you understand it, great, preach it, show everyone. But there's very few videos and textbooks about this RNG model, so it's a bit hard. Like I said, you should really only use this model for turbo machinery, compressors, turbines, high swirling flows, like vortex modeling, for an aerodynamic component, like you might want to create some vortex generators to see how that vortex is. Use this model, Now for the realizable model, now I want to say this, a lot of students think this is better than the RNG. It's not, okay? It's not worse, it's not better, it's just different, okay? This model is used when there is separation of the flows, okay? Or complex flow features, okay? So let's talk about the separation of the flows. So think of an airfoil, and it's a quite complex airfoil, and you've got different separation of flows. You would use this model. While the standard epsilon model is fine for if you've got a simple airfoil and there's only one mode of separation. Hopefully that makes sense, okay? Complex flow features, this means like, are we doing multi-phase modeling? Or is it species modeling? When I say species, the combustion modeling types, And one of the reasons this model is actually great, and this is why it works, because it models any viscosity term or the dynamic viscosity term really well, It's still Boussière's hypothesis, so there's some shortcomings and whatnot, but it's still better than the standard on the RNG for that term, Because it's numerically modeled rather than given as fixed constant, One drawback to the model is if you have a rotating or stationary fluid zones directly adjacent to each other. So you have like an active mesh, And this is a new feature now in most, especially in Ansys Fluent, when you have like different mesh sizings that are dynamic. So if they change, it can have not so great readings. I spelled advantageous. I spelled that word wrong. Apologies, but the common uses are like most flow types. If you use this model instead of the k-epsilon, the standard k-epsilon, you won't go wrong. Okay. So it's okay. It's fine. It's certainly better. Also, it multi-phase modeling, species modeling. And like I said, this model is pretty great in adverse pressure gradient because of the eddy viscosity. Okay. Now, hopefully you have noticed. If not, that's fine. Hopefully you have noticed over time when we're going down, it actually becomes chronologically more expensive. So the most expensive one, in theory, is the realizable, because it's computation. You're using computers to solve the eddy viscosity. So for each volume you have, it's using this. For this one, it's a constant. If it's low Reynolds, it uses this. But not many times is low Reynolds. And for this one, this is a blank statement. For every element, for every volume of that element, use this. When I say volume of element, Ansys Fluent uses a finite volume method rather than finite element method. Okay. So some key takeaways. So TKE. So we're starting at the last. This one. TK equations are basically the exact same for the three models. They're almost identical. There may be one or two changes in the production of the terms or whatever, but just think they're exactly the same. The main difference is the generation and destruction of the dissipation of the turbulent flows. So each method brings its own unique ways to solve this problem. RNG is better for swirling flows because of the swirl factor. See, if you want more, it's another equation that for swirling factor which you have to initialize in the problem. If you want more details, go and see the theory guide for Ansys Fluent. But be warned, it is not easy. Okay, it's not an easy concept to get your head around. And also, all the equations So all the equations to use energy and the dissipation of the energy. To close the TKE and the epsilon turbulent viscosities used are different from all methods. Yeah, standard RNG are basically constants. Yeah, just think about our standard RNG are constants except for row rail number, but for the sake of this argument, they're all constants. While the realizable is numerically defined with a set of equations. Okay, so if you have if you know the fluid is highly chaotic and turbulent, you tend to want to use realizable more often. Yeah, if the flow is swirling, you want to use RNG. If the turbulence is more uniform, you can get away with using the standard. Okay. And also, another thing, all the equations have a different way of solving the turbulent Prandtl number. Yeah, this is just another parameter. You know, Mr. Louis Ludwig Prandtl, I think is his name. Did some great work in thermodynamics, fluid dynamics, stuff like that. Basically, it's just a Prandtl number, a turbulent Prandtl number of momentum and thermal dissipation. Yeah, it's just different ways of solving it. So here are my references. Okay, so standard realizable, no RNG, realizable, and oh no, sorry, standard RNG realizable. Okay, so these are actually the creators of this method. Yeah, so I would thank you for very much for listening to me talk about this. I really do appreciate it. So have a very good day, guys. Goodbye.